Yes.
Yeah.
Great. Okay, we're going to start. Here we go. So the first thing I want to talk about is this particular calculus that we're delivering to you here is called ROC calculus, and that stands for Developing and Investigating a Rigorous Approach to Conceptual Calculus. Okay, so this is going to be, for those of you who are coming from high school calculus, or you did not have direct calculus here at ASU, this course may feel different to you, and so I just want to kind of just prepare you for that. So get ready to, in this course, first of all, focus on how calculus models the real world. That's what we're all about here. That there's quantities all around us, and those quantities are accumulating at various rates of change. So our focus is going to be on accumulation and rate of change, not just slope of the tangent line and area under the curve. Those aren't going to be the emphasis in this class. Rather, any quantity can be modeled with calculus as it accumulates at a certain rate of change. Okay? Next, in this course, you're going to be expected to interpret, understand, and use symbols and expressions meaningfully. So when we're writing symbols, expressions, we always want to know what those things mean, what they represent. So we're going to be working on that and practicing our interpretation of symbols and expressions. Finally, we want to, in this class, you're going to be expected to think critically, to reason, and to make connections of concepts to solve problems. It will not emphasize memorizing methods and procedures and replicating those methods and procedures. Some of you may have had math courses like that in the past. Okay, this is not one of them. There will be a little bit of that, but we're really going to focus on your ability to solve problems, to think critically, to reason about the concepts in the class. Okay, so, and why do we do that? Because that's relevant. Okay, so just repeating procedures, moving the symbols around isn't always relevant for you as a person in your life. So, but calculus models the real world, and so that's what we're after. We're after understanding how it does, and that's relevant to you. So overall, this course, like I said, it's going to feel different. And so in order to succeed, you got to make sure you're always engaged, listening, attentive, not trying to predict what I'm going to say because you've had calculus before, but really listening to what I'm saying because it might be different. Okay, so your brain needs to be on all the time. Okay, so that's your fair warning. Let's get started. And so let me just say, in terms of questions, I gotta admit some more people into the room here. Okay, for those of you who came late, I just need to repeat this announcement. For those of you who came to the class late, I need to repeat the announcement. When you log into Zoom, you need to log in with your ASU email address. If you're logging in, you can't log in with a different email address, or else I have to admit you manually, and I don't have time for that with 100 students. So everyone needs to log into Zoom starting Monday with your ASU address. Okay, so as I was saying, in terms of questions, if you can just interject verbally to ask a question, I'm okay with that. I know there's lots of us. If you end up getting cut off by someone, just wait for an open moment and then ask your question then. Okay, here we go. All right, so in Calc 1, you investigated two primary problems in the subject of calculus. And the first, so whether you knew it or not, this is what you were doing. So you know how much of a quantity you have at every moment, and you want to know how fast that quantity is changing at every moment. This was one of the things you were looking at in a broad, general kind of sense. And then the other thing was, you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. So it's kind of the flip. It's the reverse of the first. So all of basic elementary calculus kind of boils down to these two problems, or these two endeavors, okay? And so in Calc 2, we will explore both, but really the emphasis is on endeavor number 2, okay? So we're going to do a crash course of Calc 1 in this first week or week and a half. We're going to review this endeavor or this problem, kind of just to review it and also review it in this this mode, or this way of thinking that is Dirac calculus, right? This modeling the real world with rate of change and accumulation. All right, so you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. So I'm going to break this down into a series of principles. We're going to review that, and I'm going to give you a series of principles, and kind of as an underlying principle before we start is principle 0, and that's that variables vary. Okay, variables vary. So here's an equation, 2x minus 7, and when you see that equation, what comes to mind maybe, oh, I need to solve that and find the value of x, right? And so you may be thinking x equals 3.5. When you see 2x minus 7 equals 0, you think, oh, x equals 3.5, okay? And that's natural. You've been trained for years to solve equations. All right, so the question is, could x be 4 or 10 or negative 0.5? Could it be? And so some may think, no way, it can't be. It has to be 3.5. But looking at it differently, we could say that x could be 4 or 10 or negative 0.5. And then what would happen? It's just that that equation wouldn't be true. Okay? So suppose x is defined as the number of hours elapsed since your plane left the ground. Okay, so then x takes on many values. In fact, x takes on any real number. So at some point in the flight, x would equal 4. Okay, and that would mean you're at 4 hours since you took off. All right, what about x equals negative 0.5? Does that make sense in this situation? Well, it actually does. It would mean like 30 minutes before the plane took off. Okay, so you could have, in this situation, you could have x be negative. So we think about this situation as this situation unfolded in the real world at some point. And as this whole plane taking off scenario was unfolding, x was continually varying and taking on all these different values. Then maybe x equals 3.5. Maybe that's, 3.5 hours. That was the first time that you got a snack. Okay, rough flight, right? So maybe that's what that means. That was just a particular point in time that's of interest in this flight. Okay, but we want to think of do you see my menu bar here or not?
No, I don't see a menu
bar. No, I don't see it.
Awesome.
No.
Okay, thank you very much. Okay, so I see it, but you don't. Great. All right, so we want to think of x as varying. It's taking on many values as a situation unfolds. So here I'm showing it taking on the values from -3, so 3 hours before the flight. Now it's an hour before the flight. Now it's 2.5 hours after we took off. Now it's 7 hours after we take off. X takes on every value as this situation unfolds. And then solving an equation might be some particular point of interest in the situation. Okay, what would the variable dx represent? So if x is the number of hours since we took off, what would the variable dx represent? Well, dx represents a change or a variation in the number of hours. So for instance, starting at 1.5 hours, as x is increasing, so we think about, so x is increasing from 1.6 to 3.9, and at that moment then when x is 3.9, dx has a value of 2.3 because it's the variation starting from 1.5 and ending at 1.6 and ending at 3.9. So that's a variation or a change in hours of 2.3. And then our x keeps increasing. And so now dx is a variable as well. Dx varied through all the values starting at 2.3 there up until 4.6 now. So x initial is this particular starting value of x, and then x final, a particular ending value of x. Dx would be how how many hours went by, or the change of the variation in hours. Okay, any questions on principle 0? Variables vary. And we want to think of dx also as a variable. It varies. It's an amount of change, and it varies as x varies. Okay, so principle 1 is rate of change. Principle 1. So suppose you're buying trail mix that costs $3.20 a pound. So after scooping some mix into your bag, you decide you want more. What additional cost will you pay for 1.5 more pounds of trail mix? I want everyone to figure this out. Get a calculator, get a pen and paper. Everyone find a number, but don't say what it is yet. So everyone find this. How much would you spend how much more would you have to pay? What's your additional cost if you add 1.5 more pounds of trail mix into your bag? We're all getting a number for that. Okay, and so what you should have thought was, I'm going to take my 3.2 and do what? Multiply by 1.5. And is that $4.80?
Yeah.
So the additional amount you would pay is $4.80. So what I want to do with this little situation is we want to define variables. Okay, so when we come to real world problems, we want to kind of get out of the mindset of what are the numbers and what are the formulas and how do I get an answer. Okay, so that's, and instead let's kind of pull back and say, let's model the situation and understand the situation first, because that will give you a lot more versatility to answer all kinds of questions, not just maybe the one particular question that's being asked for. Okay, and so here are some variables. X is, y is, dx is, dy is, and m. These are all symbols that we're going to use to model this problem. So we want to define these like as a verbal or a written phrase. So what is x here? So x, one way you could say is that x is the total number of pounds of mix in the bag. Okay, remember, and x varies, right? As we're filling up the bag, x is varying through different numbers of pounds. Okay, then y would be your total cost of that number of pounds. And notice what happens. Does y vary? Yeah, y varies as x varies, right? So as x increases, y is going to increase along with it. Okay, so what is dx? We talked about this in this scenario then. What is dx? X is the total number of pounds. Then dx is?
12.8.
Variation in the number of pounds.
Some variation, right? A change in the number of pounds or a variation in the number of pounds. Okay? And so like when we were putting the 1.5 more pounds of trail mix in, as the trail mix was falling into the bag, dx was changing. Dx started at 0 and it increased through all pounds up till 1.5. And then when we finished dumping the scoop, then at the end it was 1.5. Okay? All right, so dy then is the corresponding change in cost. That varied starting at 0. So we had a bunch in there, and then we started pouring more in. dy started at 0, and dy varied from 0 up to 4.8. By the time the whole scoop was dumped in, dy reached a value of 4.8. M is our constant rate of change, and that's $3.20 per pound. Okay, so
I had a question.
Sure thing.
So you said it's the constant rate of change.
Yeah.
Does it matter if it's the constant rate of change or just rate of change?
So in this scenario, we're just talking about constant rate of change. So I suppose m, in a certain situation, m could be variable and it could vary, but in this case, it doesn't.
Thank you.
Yeah, sure. Okay, so now I want you to write an expression using these variables. So using these variables, you may not use all of them, but you want to use these variables that represents this calculation that we did earlier. Okay, so we said 320 times 1.5. So 320 was our rate of change times the total additional pounds gave us an additional cost or an increase in cost of 480. So what expression using these variables would represent that calculation?
Y equals mx.
Okay, y equals mx. What do we think? Agree with that?
No, because it's
M
a
dx equals 50y.
dx times m equals.
Right, because these aren't totals, right? So x and y are total number of pounds and total cost. And these values, the 1.5 and the 4.8, are the amount of change, right? The amount of variation to our total. Okay, so I'm going to do it this way. So if 4.8 equals 3.2 times 1.5, then the 480 is actually how much our cost changed. So it's dy. And the 3.2 was our rate of change. And the 1.5 was how much our cost changed. This equation is maybe the most important thing of today's lesson. This equation right here, arguably. Okay? Lots of important stuff. This equation frames the meaning of this number. It tells us what this number means. Okay? So we could say that number means, oh, every pound costs $3.20. And that's true, but this equation gives us a much broader meaning for this. Did we change by 1 pound? No, we changed by 1.5 pounds. You could have any change in pounds, and this rate of change tells you how much the change of cost is. Not just a change of 1 pound, but you could change the number of pounds by any amount, and then you'd know how much your cost goes up. Okay, so $3.20 per pound tells you a lot more, infinitely more than 1 pound cost $3.20, right? Because it tells you how much any number of pounds costs, right? That's what dx is. Any variation in number of pounds, you would know the resulting variation in number of dollars. Okay, let's do another quick example of this. Okay, so now we're going to remove 0.4 pounds from your bag and put it back in the bin. Okay, make sure no one's looking, right? But you're going to take 0.4 pounds out, dump it back in. Okay, so what would the value, we know our dx is our change in number of pounds or variation. What would it be now? What would dx be here?
Negative 0.4.
She wants negative 0.4, right? So with variation, we can have negative values, which means decrease in the original variable. So a decrease in x means that the variation is negative. Okay. So dx is, when it's all said and done, when our little trick here is all said and done. So before we started, dx was 0, and then as we started dumping it back into the bin, it took on all the values from 0 to negative 0.4. And then when we were walking away from the trail mix bin, our dx was negative 0.4. Okay, so what about dy?
Well, dy would have to equal like negative 0.4 times 320. I mean 3.2, right?
Right. That rate of change can give us the change in cost for any change in pounds, not just one change of 1 pound, right? It's not just that 1 pound costs $3.20. It's, you know, how much the change in cost would be for any change in pounds. Here we have negative 0.4. So we're going to do our 320 times negative 0.4. And what is that? Anyone got that?
Negative 1.28.
$1.28. Negative. And again, the negative is okay. You can have a negative variation in cost, meaning your cost went down that much, right? Okay, again. And so M is still positive $3.2 per pound. Okay, questions about dy, dx?
So we just ended up using the same formula that we came up with in the last problem.
Absolutely.
To find out what dy was. Okay,
Yes,
thank you.
absolutely. Yep, dy equals
So
mdx.
what would we use just x and just y for? Since
So
you're
if we're
in this
modeling, if
scenario.
we're keeping track of the total number of pounds in the bag, or the total cost of the bag, and we're keeping track of that, then that's what those variables would be for.
So if we're like graphing it and we're like putting in a specific input of like pounds, then we would be using x, or is that still dx? Like if we were to model this on a graph.
Yeah, so it depends what you're graphing, right? So you could graph the changes, or you could graph x and y. If you're graphing the total, yeah, if you were graphing x, and that might be, that's probably the most common graph that you would see then, although it wouldn't have to be this. But if you were graphing x and y, then this would be your total pounds in the bag and the corresponding total cost.
Okay.
Okay. Okay, so as a summary here, summary of rate of change, trail mix costs $3.20 a pound. What's the meaning of $3.20 a pound, the constant rate? So before you came in today, you might say, oh, every additional pound increases the cost by $3.20. Okay, and that's a true statement, but it's a narrow meaning. It's a narrow meaning. What's a better meaning? For any change in pounds, the change in cost is $3.20 times that change in pounds. That's the strongest, broadest definition for this constant rate of change, $3.20 a pound. It tells you how much the change in cost is for any change in pounds. Okay, how are we doing? Any questions? Okay, let's do a new scenario. A soldier lowers an American flag from the top of the pole at 0.75 meters per second. A little bit different here, but same kind of idea. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? Okay, so again, I want to kind of try to stop your instinct to just start cranking calculations, grabbing the numbers and calculating something. Instead, with a scenario, we want to let's model the scenario. Let's define variables. So if I told you that y is defined as the height of the flag in meters, we want to define each variable below completely and precisely, and then state the value in this particular situation if known. Okay, so we said y is defined as the height of the flag in meters. So if we're then kind of assigning conventionally what x and m is, what would x be? What would x be?
Time.
Time in seconds.
Okay, so time in seconds. So we want to be a little more specific because I could define lots of time variables here. Time in seconds, you know, since when, right? So whenever you define a time variable, always have your initial reference. So time in seconds.
Since he began lowering the flag.
Good. Excellent, good, right? So the number of seconds since the flag left the top, or since he started lowering the flag, or something like that. Yeah. And y I already told you. That's the height of the flag in meters. Okay, so then what would dx be? Dx would be some variation in the number of seconds, or a change in the time in seconds. And likewise, dy would be the corresponding change in the height, flag's height. Okay, m is our rate of change. And so what is the value of the rate of change in this scenario?
0.75 meters per second.
Is it 0.75 meters per second?
Negative 0.75.
Negative, isn't it?
Okay, so height is defined positively upward, right? So if our height above the ground, that's our y value, is defined positively going up, and y is decreasing, the height is decreasing, then that rate is negative 0.75. Does it make sense? So this is a frame of reference situation. The frame of reference for height above the ground, positive, increases upward. So if that y value is decreasing, it's lowering, then that rate of change is negative 0.75 positive meters per second. Okay, so let's talk about x. Is the value of x known in this situation? Is x known?
Yes.
Okay, tell me what it is.
So the initial x is 0.6 seconds, and then xf, which is final, is 2.4. So dx would be 2.4 minus 0.6.
So good job.
Yes.
Okay, so yeah, so she also talked about dx.
Oh, sorry.
No, great job. That was great. All right, so x starts at 0.6 and ends at 0.24. What about just x? X varies. It takes on every value. It takes on every value starting from 0, but in this situation, it's starting at 0.6, ending at 2.4, then x takes on every value between 0.6 and 2.4. Variables vary. Okay, variables vary. And so we're just kind of pausing an initial time and pausing at a final time, and then imagining that the flag lowers over that time, and x takes on every time between 0.6 and 2.4. Okay, what about y? So do we know the value of y, the height of the flag? Say for x initial or x final. We don't know this because we don't know the initial height. Okay, I never told you what the height of the top of the pole was. So given this information I gave you, we can determine no values of y. There's no values of y that we can know here. Okay, what about dx? So when x is 0.6, what's the value of dx?
1.8.
Are we referring to dx in like what is dx when the initial value of x is still 0.6?
Yes.
And it's
yes.
also
Yep.
going to be 0, right?
0. And then dx would vary from 0 to
1.8.
1.8 seconds. So kind of one answer to this question is, oh, in this situation, dx is 1.8 seconds. It's the amount of variation from 0.6 to 2.4. That's absolutely right. That's absolutely right. dx is 1.8. But we want to take it a step further also and say, hey, look, starting from 0.6 to 2.4, dx actually varied from 0 to 1.8. Does it make sense? Okay, what about dy? Now, we didn't know any values of y. Can we know values of dy?
Yes.
dy equals, given any change in height, the change in, given any change in time, the change in height would be the constant rate times that change in time, right? Again, it tells us more than just how much the height changes in 1 second. It tells us how much the height changes in any number of seconds, in this case, 1.8 seconds. Anybody have that number, whatever that is? And that's going to be
Negative 1.35.
1.35. So in this scenario, dx, we could say is 1.8. It varied from 0 to 1.8, and then at 1.8, the change in the flag's height was negative the change in the flag height, yeah, was negative 1.35 meters, or it came down 1.35 meters. Okay. Anybody have a question? All right, let's take this to another level here. Let's take this up a notch.
Professor, can you?
Yes, please.
Okay. So for this problem, you just kind of wanted to have us recognize that the change in x could be any value between 0 to 1.8, but for this problem, we needed to use 1.8, right?
Yeah. So it's for this problem, it's 1.8. Okay. So like I said, so the change in x is definitely 1.8. It's how much time varied from that to that. But then, kind of as a side concept, as an important concept, we also want to think of dx as varying from 0 to 1.8. We're going to see that. We'll see that more in upcoming applications. But so yes, dx is 1.8, and then therefore dy is negative 1.35 meters. But I also want to just introduce you to the idea that actually dx varied as you went from 0.6 seconds to 2.4 seconds. Dx itself varied from 0 to 1.8. Does that answer it?
Yes, sir. Thank you.
Sweet. Okay. All right. So let's take this to the next. So now, what about how much does the height change from 0.6 to x seconds since the flag left the top of the pole? All right, so now that final x, we're just going to let that be x, okay? And so we're still going to use dy equals mdx, right? dy is our change in height, m is the constant rate, dx is the change in number of seconds. And so what is the change in number of seconds now?
Is the change x minus 0.6?
Sorry. Yes, exactly. Sorry, I don't know what happened to my. Let's see. Yes, dx is now final minus initial. That's how much change occurred from any number of seconds since 0.6 seconds. The amount of change is x minus 0.6. So what really I'm asking you now is, this is equivalent to asking, what is a net accumulation function for the flag's height beginning at 0.6 seconds? So what does a net accumulation function give us? It gives us, for any change in height, for any time, this function, so any time x, will give us the change in height, dy, since 0.6 seconds. How much did the height change since 0.6 seconds at any number of seconds since we started lowering the flag from the top? Okay, so this is a net accumulation function, and we can write it this way. So here's our constant rate times our change in x, and then this now is function notation, and it represents dy. But it's better than just dy, because that whole thing that I put in the box gives us the dy for a specified value of x. So I could write a sub h for 0.91. And not only would that represent a change in y, but we know exactly what change in y that represents. It's the change in y at 0.91 seconds since the flag left the top of the pole. And then consequently, our dx is 0.31 right now. So for a dx of 0.31 or 0.91 seconds after the flag left the top, this whole expression means the corresponding change in height. So this is the idea of a net accumulation function.
Wait, how are we doing accumulation without integrating anything?
Because accumulation is it's still accumulating changes. We're still changing, right? It's because we have a constant rate of change. At a constant rate of change, the height is still changing, and we're all along the way, we're accumulating changes in height. So you don't need an integral for that. Does that help?
Yeah.
Okay. All right, so let's look at graphing. Let's look at some graphing here. So this is the second principle. First principle was rate of change or constant rate of change. Second principle, net accumulation function. So we've got that same scenario that we just had. And I want to sketch the rate of change function, and I want to sketch the net accumulation function, specifically starting from 0.6 seconds. Okay, so on both axes, I'm going to have number of seconds. So both axes are the variable x, number of seconds since we started lowering the flag from the top of the pole. The units on the rate of change function are going to be the rate of change of height, and then the units on the net accumulation function are going to be the net change in height, or meters. Because we're going to meters per second here and meters here. So what will the rate of change function look like? No matter what number of seconds we're at, the rate of change is always negative 0.75. So as x goes by, so variables vary. So as x increases, we always have a rate of change of negative 0.75. Now, what will this look like? What will our net accumulation function starting from 0.6 seconds look like? So maybe to start that, we should ask what at 0.6 seconds, what is the net accumulation of height at 0.6 seconds? What would that be? Positive, 0, or negative?
0.
It's going to be 0 because specifically the net accumulation that we're asking about is the net accumulation since 0.6 seconds. So there's been no change in the height since 0.6 seconds. And then what is this graph going to look like? Is it going to be curved? Is it going to be straight? Is it going to go up? Is it going to go down? So what happens as time goes by? What are our net accumulations? So like after a second goes by, from 0.6 seconds,
Goes down.
goes down, and it goes down at a constant rate, right? It goes down at a constant rate. So this net accumulation function is going to look like this. So a point over here, say 1.6, and I don't know, get 1.6 and negative 0.75. What does that point mean? It means that, sorry, positive. 1.6 seconds after we started lowering the flag, its change in height since 0.6 seconds is negative 0.75 meters, or it's gone down 0.75 meters since 0.6 seconds. So net accumulation. Net accumulation is a change in a quantity since a particular starting point. We call that A. So A is 0.6. And so these Y values give how much change in the quantity Y since A equals 0.6 seconds.